Hello, everybody. So now we've already finished with 1D motion, so we got that. We finished with 2D motion, we got that. Now to finish with our course of kinematics. Okay, so the last topic we'll be looking at in kinematics is circular motion. Okay, circular motion is a bit more complex than these two, so please pay attention to the following video because you might get lost. This is pretty easy to get lost because we are going to start looking at some other weird concepts such as centripetal force. You know, this force, this phantom force that we all feel, but some of us uh, wrongfully call it centrifugal. And with this lesson, we'll figure out why this thing doesn't actually exist. To call this type of force centrifugal is completely wrong, okay? So please pay attention because we're about to debunk one of the biggest misconceptions in mechanics, okay? Let's call this a big misconception. Is misconception with double S, misconception. I don't know if it's one S or two S, so let's leave it with that. Or is it double S? No, it's one S. Okay, so let's continue with our class. Okay, first thing, let's see what circular motion is. This topic subdivides into two different topics. So let's call this, let's say, uniform circular motion, or in Spanish, movimiento circular uniforme. And we have uniformly accelerated circular motion. And this is movimiento circular uniformemente acelerado. Okay, these two types of motion. They are circular motions. The main difference is that here the tangential velocity, the magnitude of the tangential velocity, or we can call this the tangential speed, remains constant. Keep in mind that I am talking about the magnitude. That is super important. Okay, super important because velocity is actually changing. Okay, but the magnitude here is the thing that is going to remain constant. And here we say that the magnitude of the tangential acceleration, this thing, is also constant. So these are the two things, and this, remember, magnitude. Okay, magnitude. These are the two main differences, okay? So if this thing, in circular uniform motion, since the magnitude of the acceleration, the tangential acceleration, is constant, we can say that tangential acceleration, in this case, the magnitude of tangential acceleration, is 0. Okay? Only for this specific case. For this specific case, we have uniformly accelerated circular motion, but this thing refers to the tangential acceleration. So this thing is constant. Okay? Okay, so that is it for this. So let's do a quick recap into what acceleration actually is. So acceleration, we know, is a rate of change of velocity, right? Of velocity. Okay, so acceleration is how much my velocity is changing over a certain interval of time. Acceleration is a vector quantity. Why? Because velocity is a vector quantity. Okay, so how much is my velocity changing with respect to time? So for example, if I have a constant acceleration, magnitude, it's called magnitude, of 1 meter per second, Oh, you know what? Let's do it. Let's say 2 meters per second squared. That means that at time 0, my velocity is 0. At time equal 1, my velocity would be 2. At time equal to, my velocity would be 4. At time equal 3, my velocity would be 6. Okay, I'm talking about strictly about magnitudes right now. Magnitude, 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 magnitude. So this means that from 0 to 2, my increment in velocity was of 2 meters per second. Whoops. So I changed my velocity from 0 to 2 meters per second in 1 second, right? Therefore, this gives me an acceleration of 2 meters per second squared. From time 1 to time 2, I changed 2 meters per second in 1 second. Therefore, my acceleration from 1 to 2 was 2 meters per second squared. Okay? So on and so forth. From 4 to 6, I changed 2 meters per second in 1 second. Therefore, my acceleration is 2 meters per second squared. So this is the concept of acceleration. This is how much my velocity is changing with respect to time. So rate of change of velocity versus time. Okay? So this is very, very important for you guys to understand. If I am talking about the magnitude, I don't really care much about the direction, right? But if I am actually talking about vector quantities, if I am talking about vector quantities, my change in my acceleration implies both a change in magnitude of the velocity, so change in magnitude, but also my change in direction. So even though if I could have no change in magnitude, if I'm having changes in direction, that implies that I have a change in the vector of velocity, and therefore if the velocity vector is changing, I have acceleration. Okay, and that is even though the magnitude of the vector remains constant. Okay, so if this thing remains constant, right here, velocity vector remains constant, but there is a change in direction, I am having an acceleration. This will be more clear in a minute. Okay, so let's just picture, for example, I have here an animation that I want to show you guys that shows how a particle moves along a circle. So here it is. Okay, so don't pay attention to this red vector right here. Here I can change the magnitude of my vector, the velocity vector. This is tangential. Remember that the length of the arrow implies the magnitude of my vector. So let's say a 4. Okay? So as the particle moves along this path, this is the velocity vector that it has. There is always, at any given point, at any given moment, the velocity vector is tangential to the path. Why? Because at that instant, so let's look at when it passes this point right here. At that instant, the particle is trying to move forward. Okay? So it's simply at that instant, and that is why the velocity vector is tangential. Okay? So I want you guys to look how at every single point this velocity vector is tangential. That means that the particle wants to move at that point forward. But at the one point afterwards, so t equals, so after some certain interval of time, it continues along its path. Okay? So that is how a particle, that is how the velocity, even though it's constant velocity, uh, is going along this circular path. Okay, so now let's continue with something else. Let's do a quick graphical analysis on this thing right here. So I'm going to draw as best I can a circle. So here it goes. So let's say that that's a circle, okay? So now let's put some particle here. So at the beginning, so right here at the beginning of this movement, okay, this is the path that this particle is going to follow. So this is position 1, okay? And the velocity vector, remember, it's tangential to the path at any given point. Whoops, so let's say here, tangential, let's draw it a little bit closer. Tangential, okay? So velocity 1. So now let's look at the particle when it's around here, okay? This is P2. The velocity vector at this point will be tangential, something like that. Velocity 2. So now, for example, let's take the particle here, P3. The velocity vector will be something like that, okay? I am drawing these velocity vectors approximately the same size. They should be the same size. Why? Because the magnitude of velocity, remember that we're talking about constant movimiento circular uniforme, constant uniform circular motion. That implies that the tangential magnitude of the velocity is always constant. So that means this. Okay? So yeah, okay. But this thing, let's look at how this thing behaves. Okay, remember that acceleration is my change in velocity over a change in time. Okay, so right here we are talking that the magnitude of velocity, the magnitude of the velocity is constant. The magnitude of the velocity is constant. So should we have acceleration if the magnitude is constant? Well, yeah, because remember that acceleration is also a vectorial quantity, and it implies changes both in magnitude and direction. So since these vectors, they are not changing in magnitude, so the length of this vector remains the same, but the direction of these vectors definitely is changing, right? So this is theta 1, which is different to theta 2, which is different to theta 3, right? So the direction of these vectors is actually changing. So let's look at a graph that I found in a book. It's pretty nice. It helps us look at this. Oh, before we do that, acceleration is a change in velocity over time. And remember that this symbol, delta, implies final minus initial. So let's call this V2 minus V1 over delta t. Okay, this is acceleration. So let's look at the graph that I promised. Come on, where are you? There you are. Okay, so look, right here, it's exactly the same figure that I just drew. So we have point A, it has velocity 1, and point B has velocity 2. These velocities are tangential to the circular path, okay? Tangential, okay? So now, what we are looking at, okay, what we are looking at is that my change in velocity, so my acceleration, would be v2 minus v1. Okay, so v2 minus v1, right here, what the book is doing is finding the resulting vector through the uh, polygon analysis. So v2 minus v1, look at that. Our resultant velocity vector, the change in velocity, is somewhere going this direction. So near the center, right? So between these 2 points, the change in velocity is a resultant vector is something that goes inward, okay? It kind of goes inward. So now let's look at this in a very, very, very small change. So for that, I need to redraw my circle. Okay, so for that, I need to redraw my circle. So here it goes. So picture that that's a circle. I'm gonna take color here. So right now, what I'm going to do is I'm going to change I'm going to determine, that was what we did right here. Okay, so what we did here is my average velocity, because it's between two really far apart points, points that are far apart from each other. But now I'm going to try to take a look at my change from P1 to a point that is really close to it. So P2. Okay, so P1, you know what? I'll even put it a little bit closer. So P1, let's call this P2. So P1 has this velocity vector, and P2 has this velocity vector. Okay, so let me see. Okay, now let's reference these 2 points with respect to the center of the circle. So this is the center of the circle, this is the center of the circle. Okay, so there was a small increment here, delta theta. Okay, so if we take V1, let's say V2 minus V1. So we take these two vectors. V2 minus V1 would indicate my delta V. And we already know from the past picture that it's a vector that goes somewhat in this direction, correct? So if we make this delta theta tend to 0, okay, this thing is more and more perpendicular to this original vector. Okay, so I don't want to continue because I think the video has gotten long enough. But if we continue, if we get P2 close enough to P1, delta V, the direction that delta V will have will be perpendicular to V1. And that implies that if my resultant vector goes inward, so let's call this inward, then that will tell me that my acceleration is going inward as well. So if delta V goes inward, that implies that there is some force that is accelerating it, that there is a delta V in that direction. That means that there is an acceleration in that direction. Okay, so if there's an acceleration in that direction, that implies that there is a force that creates that acceleration. And this force, since it goes inward, is called centripetal. And this, I think this is Latin or Greek. I'm not sure. Let me see if I wrote it around here. I don't know if it's Latin or Greek, but this means center seeking. Okay, I'll explain later why you guys might feel that it goes outward. I'll put that in another video. But no, what happens really is, since this change in velocity vectors implies a vector going inwards, okay, as we saw here, here it is. As there's a vector going inwards, okay, as these two vectors get close to each other, so around here, this vector becomes more and more perpendicular to V1. So when the limit of this thing becomes really, really small, so this delta theta becomes really, really small, this delta V becomes perpendicular to this vector. So that means that the resultant vector of velocity is going here. That implies that the acceleration is going here. And if there's acceleration going here, that means that there's a force that is trying to accelerate my projectile inwards as well, okay? And that is called centripetal, okay? Center-seeking force. It is not going outwards, as you guys might think. It is going inwards. Why? Because there's a change. The change in velocity vectors implies a change inwards, okay? So I'll stop the video here because I don't want to confuse you guys. And yeah, I'll upload another video regarding the formulas that we'll be using, and then we'll do an example, okay? So cheers.